to finish up. In HiPAC, there's a lot of things in HiPAC that allow you to fix data if inside the field it wasn't collected right. Move an offset, change your draft sounding, your roll correction, hash testing, right? One of the other ones is create contours. And I don't really like these contours. We have a way of smoothing the contours into the model. Well, one more utility is we're trying to make a pretty picture at the end of the day. We're trying to make a contour sounding fun. I don't like all these little bits of contours. In the olden days, 20 years ago, the way to make contours was to hand draw them around the sound dunes. Where you have the 7s and the 8s and you draw the contour line. Well, the computer does, but it doesn't do a perfect job. So one of the little programs inside utility, there's a lot of little programs that we have. Under file work, I believe it's under file work, is a contour editor. The contour editor, I can open up a DXF file. And you can see every one of these points are one of the nodal points. The contour editor allows me to bring in my worst soundings if I want. Adjust the contours if they're pretty dense, different sides of it. So I can grab a point and move. That's an extreme example. But I can move contours around if I don't like the way it was built. I can simplify the contours. And do it a few times and really remove many of the little subtle things. I can remove nodal points if I want. I can smooth contours. I can smooth it as many times as I want, and I can change my threshold to 100. Really reduce the little bits and pieces. When I save the file, contour adjusted. And you can see I can start removing some of the sharp edges. Some of the little bits are there because it didn't hit a certain threshold. If I remove the first one, those little bits and pieces are no longer there. So this is the adjusted one versus the non-adjusted one. So if you want to make a nice contour plot, we know the soundings can fall on either side, and if it's noisy data, you're going to get something like that. We don't want to show anyone that, so we want to show someone something like that. You put some soundings on top of it. We put our background file on top of it. That just becomes a nicer picture. We can label our contours, and that was part of the tin model. But this compared to the original contour, room to grow. We have a lot of this little noise there. All this. I don't feel like that. So, and that's just one of many tools inside HiPack that you have. Geodesy, project conversion, you can correct if the geodesy is wrong. Side scan data reformat. If someone else gives us a data file from an EdgeTech or a line or someone else's file, it has to be a HiPack file for all these programs to work. But I could take a XSE or XPF and all SIMRED file and make it a HiPack type. So the HiPack is just not limited to you have to collect the data in HiPack. Someone else can collect it. Well, one last piece of information we have with these files. The HSX file, EOH end of header, there's all the information, there's the offset, that's why we can correct it and process it. Then we have our data. We looked at our position data, we looked at our motion data, we looked at the multibeam data, RMB, we're a multibeam. Range, angle, takeoff angle, intensity, and quality. So there's two more pieces of data. Besides the range and angle, we have this intensity data, and then we have RSS, raw side scan data. Backscatter in this case, we're putting in as a side scan file. So there's two more pieces of information that this sonar is giving us. The intensity value, it's mapped 0 to, I don't know if it's 8-bit or 12-bit, 0 to 4095. For side scan, again, it's just a number. In HiPack, there's two ways to handle side scan. There's side scan data. High scan and geocoder. High scan will handle the RSS, the side scan data, or a traditional side scan. Geocoder can handle this as well as the intensity data. So let's just do a simple example for high scan and what the data would look like. We'll take a line down below. So we're not in multibeam anymore, but we're in side scan, targeting mosaicing, it's called. The name of the program is HiScan.exe. We'll open up an HSX file. Maybe I'll do the last two, just to get some mosaic going on. We'll have set parameters, just like the read parameters in MB Max, but in side scan, there's really not a whole lot we can do. We can pick high, low frequency. Well, we only have one. We're only on one boat, so there's really no offsets that we have to worry about. We have the track line data, the heading data, and half the side scan imagery. The reason why we want to see half is we want that blue line our bottom track to touch the first return. This stuff in the water column, sometimes it stands up there. We don't want that. We want to get the blue line as close as possible to the first return, because we're going to seam it together. I'll show you in the next phase. Navigation line, just like before, I can window in an area and remove it. So a lot of the programs will act in the same way. There's a section, remove the section. Change the line to the next line. Grab a section and remove it. Want the blue line on the bottom, there's a spike in the data. Sometimes this adjust value does a good job. If not, see if I can actually trace the bottom any way I want. That's called bottom tracking. Some side scans are better. So we look at the data, we want to make sure the navigation's okay, like in phase one. Then we have the data itself. There's a nice scour mark going across. So this is our water column. We're going to stretch the data together to remove the water column, but traditional side scan will show that. And it's going to stretch it where the blue line is. So if the blue line was up in the middle, you'd have a hole in the data. F9 side scan controls. I can always remove the bottom column. And that's what we're going to look at. But before we go into stage 3 to actually make a pretty picture, we can change the colors. So there's no processing in side scan. There's only changing the colors and making a pretty picture. So there's a color game. Maybe we want side grayscale. Traditionally, every side scan, the inside is darker than the outside. It's a time-varying game, or it's a game problem. I can clean it up by adjusting the time-varying game. And basically, I'm going to lighten up the middle and darken up the outer edge. A lot of side scans, you have to do that. Apply to all files. And that's what our data is going to start to look like. This is our range scale. We can see the entire data set. There's probably not quite sure why I get black on the outside there. Just do one more. Again, they changed the range scale and it didn't behave very good. Not a whole lot I could do about that. If there was a rock, a lot of times side scan finds a feature. You can do some target measurements, double click on it, and start to measure out contact height. I'll have a better example after. But the whole idea is to make sure that you can see the data, clean it up, change the color. We can go to the next line. Scour marks on the bottom. Phase 3, I put the two lines together. Select files to include in the mosaic. Select the two, move it over. Next. Enter the resolution. 20 centimeters. Next. 3 megabyte file. That's doable. I won't turn any filters on just to show you what raw data would look like. And then you hit go. And that's as much as you have to do for side scan. And there's our side scan mosaic. There's a channel that the game got all messed up on. Click next to save mosaic, next, side scan 2. Exit it out. Side scan 2. And down below would be my side scan data. Now, there was a problem with the gain with the auto TVG inside the channel. But the whole idea is to a little bit more information. There's a nice scour mark down below. Where you can see on the multi-beam the scour mark, and it's trying to continue with the side scan. So it just gives you a little bit more information, the scour mark on it. Like in Cube, there's a program that does the same thing automatically. Cube, you know, we put in the HS2 files and it came out as XYZ, we didn't have to worry about anything. Well, in SideScan, there's this program called Geocoder. I'll take the same two lines.
Finish.
Try again. I don't want the log file, I just wanted 2 lines. side scan, Word data file, HSX, 3940. Comes in, make a mosaic, save a tip, and that's all I have to do for this one. There are a lot of buttons. There's bottom classification, so geocoding does other stuff. Won't do targeting. When I could go through some angular response analysis, click on the bottom and is that rock or gravel or sand, and mathematically come up with some kind of value. A little issue with the heading. Save to tip, geocoder. And what that would look like would be this. I think that's a much nicer job about the first one. So it does a nice, here's a scour mark, some kind of anchor drag mark or something. So it's a hands-off approach that handles the side scan data. You don't even see the seam in the middle. It does a better job than bottom track. So if you want to present the side scan data, high scan and geocoder will do it. Notice this feature right there. Turn geocoder up. There's a rock or something on the multibeam. Geocoder is going to come up. So it's representation of what the bottom should look like. Not a bad job, considering we don't have to do any more work. And there's one more piece of data that this redesign system has given us. When they set it up, they called it RI theta, range, intensity, and angle, LI intensity. In geocoder, it's going to be this beam time series, beam average. But I need a GSF file. Remember when we were in MB Max? One of the save options was GSF, Word data, HSX, the last two files, bring it in. Like the cube for HS2, I have to get to phase 2 to save a GSF file. I'm not going to do any edits or any corrections to it. File, save, this GSF section down here. We saved HS2, we saved XYZ. Now we're going to save GSF. Side scan, geocoder, beam average, let's see if it works. Edit file, GSF file. This is all coming from that one HSX file. It had the intensity, it had the side scan. So as much as you want to show for a final product. Save tip, intensity. So there's my geocoder side scan, scour logs, bumps. That's what my intensity would look like. Nothing very exciting. In fact, a lot of folks don't even collect that RI theta. Just fills up the file a little bit more. But how do we process it? It's in geocoder. One last thing about the side scan, I'm just using a different side scan, is the bathymetry of the multibeam measures the water depth. The side scan measures how high a contact is off the bottom. Side scan, targeting mosaicing for HSX. Time. Side scan. These are really short files, and there's a little bug in the iPad with one of the windows. Go to page 2, and I make this window just a little bit smaller. So we go down here and we see a rock at the bottom and a little bit of a shadow. Probably better not, unless I find something else really exciting. Oh, there's a better one. Okay. There's a depression, there's a rock, and the black is the shadow. The signal can't pass through the rock until it gets closer. So the proportion of how high the rock is and the angle gives us the triangle for the, I measure how far the shadow is, I know how high it is off the bottom. So the whole point of a side scan is I can double click on the object mathematically. The first one is your bottom return. The second one, I'm going to move a little triangle. Right there, the intersection between the white and the black is the intersection between the contact and the shadow. And 3 is the far edge of the shadow. So by measuring these 1, 2, and 3, I can tell that that rock is 90 centimeters high. So it's a nice visual display, but I can also do some target measurements.
Wow.
So there's another little piece of information you can have for processing the data. A lot of times you're making a sounding plot, nobody really cares about the side scan. But it's there, iPad has the tools to process it. Geocoder works well because you don't have to worry about it. Geocoder. I just can't do targeting, but it puts everything together. Side scan time series, select the file, the Word data file. Probably on par with Q in terms of the time it takes. It doesn't give me a little clock. It's going to go through. It's like, okay, I'm almost done, and then it goes to the next one. And it'll do this a few times. So about 45 seconds, I can process 7 lines of data. 7 lines of multibeam data would take me 15 or 20 minutes. So again, there's no processing. It's image enhancements. I'm just merging the data together. I can do some classification if I really wanted to. We're not going to get into that. measure this. I'll plop it down and we'll just overlay it on top. Nothing a whole lot exciting. There's some parameters I can change. There's a resolution I can change. 188 megabytes. That might be too high. I might go down to 0.5, 30 megabytes, and make the mosaic. And that's it. So it's one of those tools that you have at your disposal. You get tired of processing multi-beam data, you can process some side scan data. Let this run for a few seconds. Just because it's a nice example. This angular response analysis. So I make a mosaic, click on any section of the bottom, compare it to a calibrated bottom, a flat bottom, and it comes up with coarse silt, gravel, rock, sand. 2 little ABI. So I extract a beam pattern. I take a little section saying that's a very boring section, use that as a reference. I'm going to recalculate that beam pattern against the entire mosaic. Angular response analysis. Just color coded based upon some, nothing exciting, but ARA, view patch area. And select on a point, adjust the model, and it's a medium sand. So mathematically, you can come up with any section on the bottom. There's another section, adjust the model, silty sand. And there's a way to classify the entire bottom and make a DXF file. So now we have bathymetry, we have side scan, and we have bottom classification, all from the same data set. Because it's just this black box, like cube, you have no intermediate steps to see what is going on. One parameter wasn't set right, but you can kind of see what's going on. We're just creating this grayscale mosaic of information from the sonar. Not a perfect world, but you can see, okay, here's a case where we know that the channel ended or started right over there. We look at the side scan, we can see a different color, different intensity. Probably a hard bottom and a soft bottom. You can interpret it that way. So it's just giving us a reflectivity off the bottom, features on the bottom and rocks. I would like to challenge myself to see if we got through everything that we needed to get through. Well, welcome to IPAC. You learned that on the boat in class. Somebody else collected data, but on the boat you collected HSX and RAW. We took these HSX files and we processed them in MBMax. How we added the data, all these different features and filters. I went through an example for the patch test because the data set we had didn't have a very good example. And then we saved our data as HS2, XYZ 1 point per cell, and GSF file. We just did the GSF. We did a lot of hands-on stuff. Probably enough that you got tired of doing it. We went through some more MBMax, cube processing, how it works. You have a cube area, the nodal area, the area of influence. So it's not saving a sounding or a point, it's looking at the neighbors to come up with what the value should be. And then we compared the MBMax and cube. We wanted to see how well this automated processing does versus MBMax. Pretty close. Cloud processing, cloud view. There's one bad data point or a few data points in a data set. Bring it into cloud. You can use a little eraser to select those few points and get rid of it. Did the presentation on performance testing. How do we know to use 65 degrees or 70 degrees for a system based upon the system itself and overall performance? Every system is going to be different because the setups are different. Then we went through tin model. I do export. We'll have to do export one more thing. And mapper. That's another sort of program. So we'll do export and mapper. So in tin model, we learned contouring, export XYZ, export a matrix. The big one was a contour. The only place to contour contours is in tin model. We saw we can make XYZ in tin model, but that's gridded XYZ. We didn't really like it, so we wanted to go through sort. And mapper and sort and export gives us our sorted XYZ data. Then we went through high plot, programs to plot the data set. Learned plotting sheets, template files. And then the last little bit was side scan and back scatter processing. Data's collected, it's part of the file, let's try to use it. And we used high scan and geocoder for the mosaic. The last thing I have to do is export and map. But map is really nothing exciting, but we'll do it and export. So there's a program in final product called export. It makes our DXF files if we want. It combines XYZ files if we want. It changes XYZ files if we want. So here's an example where all data 37.5. That's my sounding data. I can make a DXF file and someone a DXF file. I show this as an example, but we'll do it again. 37.5 DXF. Under options is CAD, it's the DXF parameter, the sounding. I make my text type CAD a little bit bigger. I can make it black soundings or color-coded soundings. You can label the layer whatever I want. Make sure no one else is turned on. Right-click, CAD file. I want to bring in these soundings, but I don't want to erase everything. So I'm just going to go to the top, up in here, right-click, create a view, export. Clean slate. Right-click, add a file, DXF. It's still kind of small, but they're my soundings. I can single, double precision, decimal on them all. But it's a DXF. We look into the options. I could also export out track lines. Somebody wants this LNW, this track line that we created, as a DXF file. Plan lines, Multibeam. They're my plan lines. Well, I can't give someone this LNW file. They don't know what it means. If I look at the format itself, it's just point data. But I can always go into export export out that plan line. AutoCAD, track lines, bend circle, perpendicular label of end zone. Track line. They're my track lines. As a DXF file, not as a line file. So it's making these DXF files. One last thing that the export can do. XYZ. XYZ parameters. If I have a file that has 2 decimals and I want to change it to 1 decimal, I can put a number of decimals from 2 to 1. If there was a vertical offset that I forgot to adjust, I can put a Z offset. Convert the Z value. Make it not space delineated, but comma delineated. Or a simple thing as tin 75 and spot 10. I want to combine 2 XYZ files to a single file. 2 XYZ files. In my XYZ, there's my output format. I can change the format if I want. Number of decimals, maybe 1. Invert the Z value. Maybe I'll make a Z offset of 10. Z offset of 10. Invert. The sounding themselves were 6.8. The new XYZ is 18. Should be 16.8, but something else went on in there. But you can see I can create these XYZ files, combine them, put an offset in anything I want. So it's a nice little feature to have, but to manipulate data. That's under final products and export. So I can make XYZ, I can make DXF, user defined, any output I want. Or I can make a KML file. Remember in here, if I right-click on the file, I can make a KML. Export's the same way. Sometimes in HiPack, there's 2 ways to do things. If I right-click, export to Google Earth, I can export out anything that's highlighted, the sounding data, the tracks, the XYZ. So I would do it, have this KML file, and typically I have internet. You can plop right into internet places. And just find this one little EDI that does it, show. Sorry. I can't find it. There's an API that does, but notice the contour editor. So a lot of the stuff I went through is on that CD. Two lines of XYZ data. If I wanted to take this data and make it in a grid cell size, I wanted to make my cell 5 by 5, and I want to take the minimum sounding. Well, what's the easiest way to do it? This is what map does. We have to create a matrix file. There's a matrix file. And I want to make it a 5 by 5. Someone hands you this XYZ data set and you want to grid it differently. Tin model can do it. The map is just one more tool. Save as MTX5. Processing sounding selection macro. It's an old program, it even looks old. But like all the other programs, you can't do all the steps until you do the first step. So, and tooltips help a lot. Just open up the matrix file. Open up the matrix. 5 by 5. Open up an XYZ. Two XYZ files. Eligibility matrix setup. What do I want to put? I'm going to put one cell in that 5 by 5. Minimum, maximum, range, average, nearest to cell center, best angle, and a log file. So maybe I want to do a range, something different. So I have all these soundings. I'm going to make it into a 5 by 5 meter. What's the variation? What's the standard deviation? Min, max. And I'm going to save this to an XYZ file. Min, max. It's pretty well flat bottom, it doesn't really help. But if there was a lot of variation, you would see what's going on inside that cell, inside that area. So it's a tool more for statistics. I mean, these are all these tools that you have. But the whole idea is you're going to take a Word data file, an HSX file, and do something with it. And you're going to either make a DXF file, a sounding file, a plot file, or a size scan data file. This was the one that added 10. Anyway, that takes us through a lot of the stuff. You know, it's hard to absorb it all in the 3 days. But at least you got a feel for what it takes to process multibeam data and what you can do with the multibeam data at the end of the day. The CD you have is a training CD. If you need a key, there's an online. If you plug into the internet, there's a password you can ask for, and you can use the software, and the password changes all the time, so no one just uses the software all the time. But if you want to continue using the software, let me know. I can get you this online access. The HiPack files are just that, HiPack files. Other people might be able to read it, but working within HiPack, we can work with matrix files and HSX files. You try another program like Keras or Quincy or someone else, they're not going to handle our files. They'll handle XYZ, but it's a HiPack file format that we have. Anyway, with that, I'm open for questions. If you want to continue working on your own data sets from start to finish, see if you can take a couple of HSX files and go all the way through plotting sheets, feel free. I mean, see how far you can get, any questions, or when you get stuck, let me know. But after this, I think I feel comfortable enough that you got something out of it in terms of, it's sometimes easy to process data and sometimes it's a challenge. It depends how the data is on the boat. If it's noisy, messy data, it's going to take a lot longer to process. 6 hours worth of data, I could probably process this data set as an XYZ clean data set in about an hour. Couldn't do it any faster than an hour, even with all the filters. It's enough noise in the data that it would take me that long. I wouldn't expect you to do it in an hour, maybe 2 hours or 3 hours. But it's certainly not going to take 20 hours to process 6 hours worth of data. So it's never that scenario. Yeah. Feel free to ask questions, work on your data set, stretch your legs, walk around. But as the class goes, the structure, I think I covered everything in the initial handout. Thank you.
So I have some question. We go back about the preparation for some fire. For example, tire fire, sound velocity fire, and maybe raw multibeam fire from the collect data on boards.
Mm-hmm.
What we get on board and how we input inside this software. That's the first step.
So what do you get on board the board in terms of?
What we get from the equipment from the boards on
okay.
boards. Yeah.
Well, on the boat, they might just hand you an HSX file. Because inside this file has all the offsets. The HSX file might have sound velocity. If not, you have to make your own sound velocity file.
Sound velocity.
Processing set down. It's as simple as 0, 1500, 1 meter, 1501. As a manual entry. It would take a while, but it's certainly doable this way. 1500. But the import function allows us to automatically import the data. You can parse it out. But you want to create a depth and a sound velocity from the sound velocity profile. If it's not part of the file, you're going to have to know it, because you can't process the data without this. You can process it, well, there'll be some errors.
And I know that we get sound velocity from the sound profile, and we get the taste file.
What?
We have a taste file.
There's
Text.
text file.
Yeah, text
Right.
file of sound velocity, and how we convert from that file to
Sound velocity, sound velocity. There's a file import button. File import.
Yeah.
There's my text file.
Yeah.
Now, if there's some header information, I'm going to skip it. 12.03 looks like a depth record. 1530 looks like a good record. I'm going to accept it. If it was this column, something down there, I would accept that one. But I'm looking for 2 columns. I'm going to accept the record. And I'm going to accept all these records. I can accept them all. And it automatically, puts one in one column and puts the sound velocity in the other column. You don't need, well, someone's giving you the data, but if you were collecting the data, you probably don't need every 3 centimeters a sound velocity value. First off, the program would only handle 512 or a certain number. So in 50 meters of water, I'm going to run out of my columns. Let's see how far this is at 3 centimeters. No, we're okay. $230 points. So 230 points in 12 meters of water. Typically, your surveys are going to be 20 or 30 or 40 meters. HiPAC only handles a certain amount. So a lot of times, when you're dropping the probe, you collect it at twice a second, or every half a meter, or every meter. But they collect it every 4 centimeters, which is pretty tight. You might see this little jitter. That's only because the probe itself is fluctuating at some uncertainty. If you have sound velocity 1, header, info. How am I going to do this easily? No. Header, watch this. Replace base 1, 5, 3 with BBC space 153. So here's our sound velocity that has some header, it has a depth, it has another field which we're going to ignore, and a sound velocity value. Someone hands you this file. File save as new SV file. Well, I'm not going to type in each one of these points, but I'm just going to ignore that ABC. Final product, processing, sound velocity, file import, new sound velocity file. Well, SV1, it's a text file, it's a header. I'm going to ignore that, skip the record. Header info, I'm going to skip that one. Now let's look what happens. It has 12, which is the depth, and 1530, which is my sound velocity. So I'm just going to check, not this one, but this one. Accept. I'm going to accept all the records. Did I not write the right one? But you would pick and choose. Somehow I lost my data. Hold on.
Okay. Okay, it's okay.
Here's all that.
Yeah, it's okay.
Now let's try it one more time. The idea is that we can pick and choose which columns that we want. It's not, doesn't have to be the first two. It could be the first and the third file import. Skip, accept all. There we go. It looks just like before. So you're going to have this text file. They're not going to give you a VEL file. They'll give you a CTD, a conductivity, temperature, depth, graphical display, sound velocity display, something. You need depth and sound velocity. They give you sound velocity and depth. We just swap the columns. That's not a problem. Swap the columns that way. They give it to you in meters. I can change my meters to feet. And go vice versa, back to feet. But your work units up on top, depth is in meters. All your items need to be in meters. Probably not so much for you, but back home, some folks work in feet, some work in meters. It's the ones that do the distance in meters and the depth in feet, and it gets all weird. Working in feet completely just makes everything so much easier. The other thing you would need is in a tide file. Multi-day or single-day tide. 8 o'clock in the morning, the tide correction, -3. At noontime or 12, 10, whatever, down to 0. At 4 in the afternoon, not a high tide. At 2100, it's a low tide. And at 23:55, it's starting to make a tide file that way. So you can put in every 5 minutes if you want. Tides aren't going to change that much. Every hour. It's going to create a TDX file and a TID file. The TID file is the one that every Max uses. It does it automatically. You don't have to worry about it. Remember, if you went before 8 o'clock, instead of the day before, -2300, 0. And that gets me between midnight and 8 o'clock in the morning, some kind of graphical display. If you don't have 5 points, I can't do a spline. You get some kind of weird curve or a straight line curve. So you have this tide file, sound velocity file. That's where I said, before we start processing data, those are the 2 files that you need. So I have to, using online survey notes, you need some notes. Create the sound velocity, VEL, and tide file before starting MBMax, because MBMax says, what are the file names? And then ask yourself the questions. I mean, what's your survey depth? It allows you to do better filtering, minimum, maximum depth. It allows you to change your color scales a little bit better. So processing sound velocity, I can either enter them or import them. I want to see some kind of graphical display. For the tides, I have my manual tides. TID is a work file. Sorry, is a use file in MBMax. TDX is the entries. So these 5 entries would be a TDX file. Once you save it, it comes out as a TID file. You end up carrying both.
Okay.
So those are the 2 that you need. Then you go into MBMax. You could always do auto processing, but it's probably the best idea to look at the data. Go into phase 1, phase 2, and then in phase 3, save HS2s, save XYZs. You should always save HS2 files. You can always go back and re-edit. Data, HSX, banding file. Processing it. I make a hole in the data, and I forgot there's a hole in the data, and I save it. Save it as an HS2. I got to check this data. Someone else wants to check my work. MBMax, open up not an HSX file, but we're going to open up an HS2 file. And they're stored in the edit directory, not in the Word directory. It's on the 14th, 10, 11. This one. Everything looks the same. But the edits are remembered. So if I go into phase 2, I have this big hole of data. It's there. It's like, well, I really want my data back. As long as I'm in the default mode, not the fast mode, I can window in an area. Select the first icon, window in an area, and re-accept the data. There's my data back. So you really never deleting points, you just flag them. That's why it's always a good idea to save HS2 files. So everybody can process data, right? Yeah.
Because we do the multibeam sounding at different time with the side scan sonar. So how we mix together multibeam sounding and side scan sonar data?
The sounding and the side scan data isn't a problem. We would look at so here's my sounding data, sort 75. Sounding. And I look at my side scan data. Let me change the color of my soundings. Where are my colors? How do I want to have white soundings, not black soundings. I want some other color. How would you do that? Well, think about it. Let's say colors over there. And if I right click on the color over here, I can say set the color. And I'm going to set the colors to yellow. Well, it's still black. I go into settings under sounding, color not by black, but by file type, or color by file. I remember I set it to the yellow color. There's my soundings in on top of my side scan. So I can put soundings and contours on top of the side scan. If you want to change the color of the sounding, they can be black, they can be color coded. If I right click, set the color, then I want to color by the file type. I press the wrong button, I want to press the other one. So here's the case where I have side scan and sounding. In tin model, I can put the two of them next to each other. I can have my soundings next to my thing, next to my data. I wanted to drape my bathymetry, or drape my side scan over the bathymetry. We have that 3D terrain view. We're on 1.1%. Might work. I need a TFW file. I just can't have an embedded file. So it might or might not work. Okay. Didn't like it. But this is where you can drape your side scan over the imagery of that body. So putting data sets together, it's a layering system, it's a GIS system. Which layer do you want? What colors do I want? So in that case, we can do it that way. And all these things can be plotted out. If you forgot how to run iPlot, file, print screen, into screen capture of the whole data. Wanted to make a file. Someone said, well, I want this side scan data. I know it's a TIFF file, but I wanted to have two pieces of information and export out as a TIFF. So I wanted to hand someone a single file that contained this information. Well, use this icon up there. We can create that arrow with a couple of colors. Select on this one, window in whatever you want. Resolution, I'm making it a georeference TIFF. I'm going to say resolution 1, save, OK. Output. New preview. Start with a clean slate. How do I know it's a TIFF output? Right click, add a file, it's a TIFF file. TIFF output. And there's on my screen an XY georeference. I even have the track line on it. So anything I saw on the screen, I was able to capture and make a georeference TIFF file. Outside, iPlot's going to make a bitmap or PDF. But if somebody wants a TIFF file of a whole bunch of layers together, that's how you can do it. So it's that icon, a little arrow, window in, set your resolution, whatever you see on the screen, that'll be your TIFF file. So it's a nice way of combining files and handing someone all these different XYZ or individual TIFF files. So something like this, and I wanted to do, take off my hash marks. Somebody wanted something like this as a TIFF file. Window in, this section right there. Resolution 1. Save. Okay. Shoot. And what that looks like, right click, add a file, TIFF, output 2. And that's what I created. It's a georeferenced TIFF file with all the different layers put together. The better the resolution, the better the little speech dot. I didn't want to make a half meter or anything like that, but you can see that you can get a really nice picture. If somebody said, okay, I need to bring this into some other spatial database, but I needed a proper XY. It puts it in the right spot. So it's a layering thing. Put any layer you want, create a TIFF image, and output it that way. Be careful though, when you get something like that, and said, okay, I want to create a TIFF on this entire thing, make your own chart. Say I want it 1 meter and refresh. The file gets really big. So keep an eye on the file size, depending on what you have. We have this huge area. Where's my data? It's kind of messy. I know it's over there, but I didn't know where it was. Figure out the file it's on, or one of the files. So maybe the matrix file. If I right click, zoom extents, it puts you around the middle. You can zoom out a little bit, do the same thing. Maybe I'll grab some of the shoreline. 1. With shoreline. Add a file, TIFF, with shoreline data. Still see the data, but you can get a little bit more of the shoreline if there was. Whatever was on the estimate set. A lot of ways to make an output final product for someone. Remember when you give someone an XYZ sounding plot, the chip runs around, you process the data, better be sure it's okay. And if you're not, put a little text bar saying, not for navigation purposes. A lot of samples we have, you see this not for navigation, because you don't want to give someone a chart, an article chart, and say, okay, well, this is what you can use. So if you're just trying to make a picture to show someone the data, to be safe, just put this not for navigation disclaimer on it.
Excuse me, we have in the Windows Explorer in the iPad project, in this folder we have HSX and raw file. How do we get this file? It's automatically we get from iPad, or we need to prepare anything?
You automatically get the HSX, REW, and a log file.
And the Multibeam sounding data and size controller already included in this?
Yes. Inside the HSX, I'll open up.
Oh, okay. We don't need to prepare anything. We just automatically get from the iPad survey module.
Word data file. So when you hit start logging on the boat, you're going to get the 2 files, REW and HSX. Move this over for a second. The raw data file, the purpose of a raw data file is to grab the GPS, the GGA message, there's the latitude, 137 east, longitude that geodesy engine does something with it, and it comes out with a POS, X and Y. If you're running single beam, it would go inside this file. But for multi-beam, the only job the raw file does is it grabs a NEMA string, makes it an XY, sends it over automatically to HiPack or HiSweep into the HSX file, and there's my POS, X and Y. That's how it gets to navigation. We look inside the record itself, there's a raw multi-beam. 6 to, you get your lesson in number 6 to 6. This one. RMB 301BL1. 1B is it's binary, but it has range, angle, intensity. This first value, this first chunk of data, this is one ping of data, has 256 ranges. It starts out, supposed to be big, 18, 18, 17, 10, 8, 6, and then gets back to 18. So we're talking one ping of data. From left to right, the range is 18 meters. Down here might be 14 meters. Down at Nada might be 10 meters, 14 and 18. So it starts off large, gets to a minimum, and then gets large again. The next chunk of data is the 75 to 75. That's the angle. We started out at 75 degrees. We go to 74 and a half, 73, down to 0, to minus 75. It might be a minus sign. It's absolute value. But that's the angle. So every less than every quarter of a degree or half a degree, there's an angle. So there's a range angle. There's a takeoff for spherical coordinates, 90 and plus 90. Then we have these 4s and 5s and 9s. R, I, theta, the intensity, that's the intensity value. And then we have quality values, 0, 1, 2, and 3s. And all this is one ping, and the system pings 40 times a second. So you're going to get this 40 times a second, each multi-beam ping. The side scan RSS, port channel, and starboard channel. So each ping of data is going to hold that much information. That's why the file gets big. That's one multi-beam ping, bathymetry and the side scan intensity. Heave is there, gyro is there, tide is there, position is there. At the end of a file, you always see a fix. It ends a nice little bookmark at the end of the page. MBMax is going to interpret the range and the angle. You don't have to worry about it. That's why off the boat, you're going to get a raw file. You throw it away in processing. Its job is to give a position to the HSX file, and the HSX file has all the other information for processing. The only thing you need off the boat might be a sound velocity cast, a tide file, if you know what the tides are, and the survey notes, so you know what happened during the survey. Other than that, you can process the data. You don't need anything else. I take it for granted. I've been doing it for a while. at least processing data. So sometimes it's easy, but it's nothing that can't be learned after enough times doing it, pressing buttons. You know how to do it. Well, at least you can figure out, I'm not supposed to press this button, I might have to press a different button.
Okay.
Everybody becomes expert multibeam users now.
Spot.
Yes. Side scan.
Yes.
Okay, maybe guys. So maybe you have a homework to create a sounding chart and contour map, right? ですよね。彼らそれを知ってるんですよね。それを作んなきゃいけない。
Yes, yes.
Okay. Would you please create yourself the program